like the background.
We good to go?
Yeah. I don't know why this is not starting.
Oh, okay. Hi everyone, we are the blue team and this is our P1 proposal. So everyone's already talked a little bit about the interpretation of the task. We're going to try and focus on kind of the key things that we took away when looking at the task description. The main thing that we're kind of worried about or want to account for is the dynamic waypoints. The idea that you can get a list of waypoints that you need to navigate through, and then at some point during your navigation, that's going to change. We need to be able to say, hey, once that changes, we're able to just change nothing and be able to account for it. Not change nothing, but go through our normal set of steps and account for it. We also need to interpret all the sensor information because we're just getting these F and B values, which are kind of just telling us offset from a line and not exactly our position. We need to be able to convert that into information that is useful for us that can help us navigate to the next waypoint. And then of course the difference between simulation and reality. If we can simulate a system that works, that's great, but there's going to be some differences between how a robot moves in a simulation versus how it moves in reality, and so we want to account for those too. Here's a general design. We're making a differential drive buggy. So differential drive means that we have two wheels. Each wheel is independently controlled by its own motor, and so that allows us to move. If we want to move forward, we can send both motors in the same direction. If we want to turn on a point, we can send one motor in one direction, the other motor in the other direction, and it'll just kind of spin. Because there's always 3 points of contact, we want to make sure that there's an extra point so that we're not kind of like flopping all over. So we're going to either use some ball bearings, or if we can keep within the material restrictions, just some low friction material that's slightly above where the wheels come down to. The idea being that when you're accelerating forward, when you're accelerating in this direction, this point will hit. If you're accelerating in this direction, this point will hit. Okay, let's get to our first control scheme, which is rotating the coordinates. The states that we are concerned about are the X and Y position of our robot, the current rotation of our robot, the waypoint list, which is constantly being updated, and then something called the stacked rotation matrix, which will make a little more sense in a bit. Abilities or our motions are to move either forward or backwards in a straight line, or theoretically in a straight line. It won't actually be straight. Our in-place spinning, so either turning left or right and by how much. Stop, which just means like temporarily halt your position, and then when you want to move again, you can give another move position, and then get waypoints. Anytime a waypoint is updated, we want to be able to get those waypoints. Okay, this is where I should mention that we made a classic blunder, which is starting our presentation before looking at the Canvas assignment page, and we learned that you can only have 3 slides per design. And so when we realized we had made all these flow charts and graphics and drawings, and we're like, okay, well, it would be a shame to waste all this. We kind of turned a bunch of slides into a single animated slide. The problem with this is that when you turn it into a PDF, some of the slides get hidden. And so to remedy that, we put all the slides that get hidden at the end of the presentation so that when you read the PDF, it is still 3 slides in this part, but there's the rest of the slides are in the other part. Okay, let's get into this. So here's the general flow of what we're gonna do. We start by manually moving to waypoint 0. In reality, we probably wanna try and angle our robot as far along the spine as possible, but for the sake of making a good visual demonstration, let's just say we just move straight south to north. Our robot comes here. We then obtain all the waypoints. It's just gonna be like a list of coordinates that are based in centimeters. And then what we want to do is rotate this whole system so that the distance, so that when we're moving from waypoint 0 to waypoint 1, it's just along the x-axis. And so we can use a linear rotation transform to do that. And if we really want to, get crazy with it, we can then subtract these the coordinates of the point we started at, so that this is 0, 0. Importantly, we don't want to save the subtraction. We only want to save the rotation, because with rotation matrices, you can kind of multiply them by each other to save all the full transform, which will allow us, whenever a new waypoint is added, to just feed it through that set of transforms to get its new coordinate in the rotated system. This will also create the effect that our y coordinate is now just our offset along the F and B directions, and our x direction is just the total distance to our next waypoint. So we'll start by moving forward a distance d. How do we figure out what we expect d to be? Well, we set up some experimental procedures. The idea being that we can tell our robot through code, move forward, X number of steps, move forward for an X amount of time, and then we're able to kind of work backwards, take the physical data that we're able to collect, create a linear regression plot, and figure out exactly how much we're moving each time we tell it to move X amount. Once we move forward, we'll get these F and B values, and then we can start doing some nice trigonometry. So the idea will be that the center of the robot is positioned in between the B and the F position. So if you want to create a triangle, we can look at these two distances and we can find the midpoint between F and B. And then once we can isolate that, we can use the fact that we already have the F plus B divided by 2 value and the D value to solve for theta and solve for L1. Once we get these values, we can update our states with everything that we've done so far. And then we can subtract the current distance that we've traveled, this L1, from the L total, which is our previously calculated X distance. This gives us a remainder distance that we still have to travel. Now we have to figure out how exactly we want to turn to arrive there. So we already know that in order to make our path parallel to the line we want to travel, we have to reverse the turn that we've currently made, or reverse the path that we've currently taken to get off course. And then we need an additional term, this is theta t, but we can calculate theta t because this line is parallel to this line, and so we have this cross section, this angle is equal to this angle, do some nice trig, and that should give us an approximation of where we're going to travel. Once we have an idea of how much we want to turn, then we can do another system where we basically take experiments to figure out how much turn we get from telling our wheels to turn for X amount of time or for X number of steps. We try and actuate the turn. In reality, we're probably not going to be perfect, but we can always keep doing the system over and over again, creating new triangles with new base points based off of how far we've projected to move. The idea being that we can kind of inch forward. Once we do this, we're repeating it. The idea being that the only two waypoints you care about at any given point in time are the previous waypoint and the next waypoint. This kind of accounts for the fact that if you add a new waypoint or change the location of a waypoint that's not in the immediate future, so like the second waypoint, it shouldn't affect anything because you can always run it through that set of rotation transforms. Some expected issues. The robot tag, this kind of assumes that the robot tag is perfectly centered on the actual tag when you get this update message, which is not going to be true. It's going to be slightly offset in some direction, and so we want to make sure that we can avoid that error accumulating over time. I think this relates a little to what the research paper we read is, so we'll save a little bit about that for now. Another thing is kind of what the previous team had been talking about with getting off course and getting maybe 2 zero values or incorrect readings. Theoretically, if we have the coordinates in our rotated matrix, that shouldn't be an issue, but in case it is, we can kind of do, because our robot is able to move forward the same that's able to move backwards, we can kind of do this wiggle motion. We move forward a little bit, then we move backwards slightly further, then we move forward slightly further, and there should always be a point, unless you're exactly perpendicular, where you start getting readings. If you are exactly perpendicular, that's an edge case, and that's something we'd have to code in. And then of course the inconsistent code motion relationship. That's basically taking what we code, and it's not always going to have the same amount of friction based off where we are in the math, so we have to be able to account for that.
Okay, so now going on to our second control scheme, which just uses proportional feedback to navigate from waypoint to waypoint. We'll have 3 main state machine modes, which is line following, waypoint turn, and recovery. We'll go more into this in the future. So to start with our state, we'll have F and D, which are the values from the front and back sensors. We'll have a list of the current waypoints. We'll have a previous waypoint list to compare to the current waypoint list. We'll have the current mode, which is follow line, waypoint turn, and recovery. And then a recovery search step, which is just a counter to manage a box search pattern that we'll use during recovery, and we'll go more into depth later. For actions, we'll have set wheel speeds, where we'll be able to set the left wheel speed and the right wheel speed independently. We'll have a turn in place, where we turn some set angle based on our wheel size. We'll have move straight distance, and then stop, which stops the robot. For state estimation, we'll get JSON packets, which we'll read, and this will give us the F, B, and then the waypoint list. We'll pass F and B through a low-pass filter to smooth out noise before use. Some errors that could come from this are latency issues, and the lighting conditions from the camera might not be make the tags readable, and then some packet loss issues. We'll also have a last waypoint list, which will just have the waypoint list from the previous cycle. So for a high-level overview of how we switch between different states would be, if the waypoint list length is less than the size of the previous waypoint list length, then we can go into the waypoint turn, because that means that we've reached the waypoint and we'll start heading towards the next one. Otherwise, we check if we are, if the F and B values are less than 10, or kind of lost from the line. If that's true, then we'll go into recovery mode and try to find the line again. Otherwise, we just resume follow line until we are able to get to the next waypoint and keep
So follow line can work if one of f or b is 0?
And.
Yeah, so the and condition can become false if one of the conditions is true. So let's say your f is 240 and your b is 0. Will your line following behavior work?
No, then it would go into recovery mode.
But the and condition isn't met. Right?
Well,
there's an edge case you're missing here, which is when one of the sensors has a reading and the other doesn't.
Okay.
And, you know, is it the general recovery mode of I'm completely lost, or is it a different recovery mode that you need when one sensor is on the line and the other isn't? Okay.
Okay, yeah. So just more detailed of what happens in the different modes. So we'll have line following, which will calculate the errors. So there will be an angle error with the difference between F and B. If it's positive, it means that we're pointing away from the line. If it's negative, it means that we're pointing towards the line. Then we'll have an offset error, which is just the max value 255 minus the average of F and B. This will tell us how far away from the line we are. So it reduces the error. If the angle error is 0, it could mean that it does mean that we're parallel to the line, but we could be offset some distance. So this is what the offset error is accounting for. And then to add them all up together, we have a total error, which will have the angle error multiplied by a weight added to the offset error multiplied by a weight. And then that total error will be used in the steering adjustment, where we'll have a proportional variable that we'll have to tune to figure out how much we actually need to steer. And then to do this, we just have left speed, right speed, which is just base speed plus or minus the steering adjustment, and we can set the wheel speeds to account for that steering adjustment. So once we've reached the waypoint, we need to be able to turn to kind of point us towards the next waypoint. And to do this, we'll have an incoming vector and then an outgoing vector. This is just used by taking for the incoming vector, this is used for taking current waypoint minus previous waypoint, and then for outgoing, it's next waypoint minus current waypoint. We can do some calculations with trig, and then figure out the angle theta that we need to turn. And then we can also use the cross product to figure out if we need to turn counterclockwise or clockwise. And once we have those calculations, we can turn in place, move straight, and then transition to line following.
So let me point out that here you have not verified your three conditions for follow line. That is, you might enter follow line with both of the sensors being 0. Right? Because you haven't checked.
Yeah. And this is the recovery mode. If we get lost, we'll stop. We'll move backwards -15 to, or this is just a variable. We have to figure it out through testing. And then we'll initiate a box search where we just turn, move forward to set distance D. And then if we haven't found it yet, turn again, move forward to set distance D. And then if we haven't found it yet, we'll turn again, move forward 2D, and then this will continue expanding. This just keeps going until follow line is detected.
Okay, so based on our design, we try to look at some of the papers that we can solve some issues that we might be encountering with the odometry error calibration. So our design is based on this baggy differential robot. So maybe there might be some challenges or some errors with the small repeatable geometry errors, like one of the windows should be slightly bigger than the other, or maybe the axis length being off, so making some odometry drift inconsistently. So then there's this classical method known as the UMB mark, which gives a simple way to measure these errors and compute some small correction factors so that our dead reckoning stays closer to the truth. So what this UMB mark does is that we first drive a square of known size length both clockwise and anti-clockwise, then we call the final Boole's errors. So then the clockwise and anti-clockwise difference separate two main biases, which is the unequal view dimensions and the non-effective ways. So what we need to compute, or some of the parameters that we need to do is that we need a per wheel scale factors to fit the straight line bias from the diameter mismatch, right, based on our design. Then also we need a corrected axle length to fix the 10 rating scale. So how fast the robots rotate for a given line, for a given right and left turn. So based on this, the method that we're going to use, I'm going to measure these biases with a simple experiment and then write the corrected parameters back into the volumetric class. So then minus colleague will now explain the method into details.
So I will present the details of this method. So first we set up a square path with like a 4x4 meter square, and the path is like straight segment and stop, and then in place 90 degrees turn. Run this robot slow and to avoid sleep. And then we run multiple clockwise and counterclockwise trials and record the return arrows delta x and the delta y near the start point. Like here, this is start point, and then after one square pass, and then there's a gap difference between the end and start. And then we compute the centroids of both clusters, and the sum reflects the turn angle bias, which is wheel-based arrow, and the difference reflects straight line drift, which is diameter arrow. And so for effective wheelbase, the actual and the wheel ratio dr over dl. And before this, we first need to do a scale calibration, the straight line scale k. And then we write back to the odometry formula. And then the systematic error will drop significantly, often by the order of magnitude. And the other random drift will fused by some vision and LiDAR devices. And how can this fit in our pipeline? We need to add a short pre-mission calibration before demo 2, because demo 1 simulation we couldn't do that. And then we can get the wheel ratio dr over dl and the per wheel scale and the effective wheelbase straight line scale k, and fit those into our control scheme 1 or 2 maybe. Then we can remove the systematic bias. So waypoint logic relies on accurate odometry rather than constant corrective steering. So this is the reference of this method. And our weekly meeting schedule is Thursday directly after class, and also Friday around 4 p.m. That's thank you.
So a couple of things.